We now cover section 3.2, linear independence and the concept of basis. This is a little bit long section and it covers the very important building blocks of vector spaces. First, a definition. A finite list of vectors denoted by v1, v2, and so on up to vm. So this is a finite list. In a vector space, V is called linearly independent if the sum as I goes from 1 to m of ai vi equals to 0 vector. So now I want to emphasize that ai's are scalars and vi's are vectors, equals to the 0 vector only if all the coefficients a1, a2, and so on up to am equals to 0. Let me remind you that this sum of scalar multiples of vectors v1, v2 through vm, I call these, and many other books call these, linear combinations of the list v1, v2, vm. Also, there is another definition: 0 times v1 plus 0 times v2 plus 0 times vm. I could also write this, of course, 0 coefficient times vi and the summation as I goes from 1 to m, which is of course 0 vector. And this is called trivial linear combination. So another way to say linearly independent vectors, list of vectors, is that that is v1, vm, also we used the notation L before, is a linearly independent list if and only if, that's by definition, only the trivial linear combination results in 0 vector. Sometimes instead of a list, I should remind you that means ordered list. Sometimes instead of a list, an ordered list, you want to talk about set in general. So this is another definition. A finite set S of V is linearly independent if all list of distinct vectors from S is linearly independent. So a few comments about this. Let me remind everybody that as an example, we could have a set like S with repeated elements v1, v1, v2. We don't usually do this, but this is not against the definition of a set. But then what happens is that this set is the same as v1, v2. So we don't usually write out repeated elements. We just usually use the notation by writing down one element only once. On the other hand, a set S doesn't have to be ordered. That means that if we have a set with two vectors v1 and v2, we consider this to be the same as the set with vectors v2 and v1. We don't care about orders when we talk about sets. So this was a set. Instead of that, if we consider a list, the list has in its definition that it's supposed to be ordered. So that means that this list with v1, v2 in this order is not the same as the list with vectors in the order v2 and v1. And also neither of these equal to the list with v1, v1, v2 with repeated elements. Linearly independent. So the independent is already a negation of dependence, and then we will turn this around and negate it one more time. So if a set or list is not linearly independent, then it is called linearly dependent. linearly dependent. And then by definition of the negation of the statement that only the trivial linear combination gives 0, that means a non-trivial linear combination can produce or can result in the 0 vector. So let's see examples for that, how this is possible to have linearly dependent list. Well, in general, if we have, for example, a repetition in a list, this will be always linearly dependent. When you think about linearly dependent lists, you have to think what kind of linear combination A1, V1, and in this case V2 is V1, so plus A2, V1. What kind of linear combination could produce the 0 vector? And the question is what kind of coefficients we can choose for that. Well, if you have V1 and another V1, one way to create 0 from those is if you cancel them with each other. So for example, we could have 2V1 for one coefficient and then minus 2V1, so minus 2 coefficient for the other, and of course that will give you the 0 vector. So that shows that they are linearly dependent because you can come up with non-zero coefficients. That means non-trivial linear combination that gives you a 0 vector. And of course there are many different ways to do that. You could just put 1v1 and minus v1. Another example, instead of a list, of course we could have also a set the same way, but instead of repetition in a set now, so this was a list, now let's consider a set, 0 v, we don't care what kind of v this is, it doesn't have to be 0 vector, so this will be linearly dependent no matter what v is. If you have a 0 vector in a set, why is it linearly dependent? Well, again, the same idea as before. You have to come up with not all 0 coefficients that creates 0 vector from a linear combination. And then, so we already know that from an old lemma from chapter 2, that if you have a 0 vector multiplied with a scalar, that will always give you the 0 vector. So then that means that this other part should be also 0. How can we make it 0? In this first one, it doesn't matter what A1 is. So for example, we could choose A1 equals 3. For the second one, so if you have 0 plus another vector equals 0 vector, then this must be the 0 vector. Since we don't know what v is, we have to set A2 to be 0, the scalar. But this is fine because A1 is not 0, so that means we have 3 0 vector plus 0 v vector equals to the 0 vector, and that means that we have coefficients 3 and 0, and this is already non-trivial because at least one coefficient is not 0. Non-trivial linear combination, because at least one of the coefficients is not 0, produces the 0 vector. So that means it's linearly dependent. So what you can see here is that a set with a 0 vector in it will be always linearly dependent. Also a list, of course. Let's see another example now for R2 vectors. And let's look at the list that we looked before, the 1, 0 vector and 0, 1 vector. So the question is this linearly independent or dependent? Let's look at linear combinations and how can we get 0. So A1, 1, 0 plus A2, 0, 1. How can this be the 0 vector? What kind of A's could we choose? Can we choose non-trivial, non-zero A's? Can we have at least some non-zero A's? Let's see. we know how to do in R2 vectors. Scalar multiplication, it goes component by component, but the second component in this first vector is 0, so a1 times 0 is 0, a1 times 1 is 1. The second vector will be 0, and the second component will be a2. Then we also know how to add together vectors, component by component, so we have a1 plus 0, a1, 0 plus a2, a2. That must be the 0 vector, if the linear combination gives the 0 vector. And we compare vectors component by component, so that means that a1 is 0 and a2 is 0. That means it must be the case. That means only the trivial linear combination produces 0 vector. And that means that the list 0, 1, yeah, I changed the order, 1, 0, 0, 1 vectors is linearly independent. So we have a big lemma in this section, lemma 3.2.1. It's called the linear dependence lemma, and it says that if you have L, a list v1, v2, vm vectors, and it's a non-empty list of non-zero vectors, then the following are equivalent. First, L is linearly dependent. Second, there is some index j greater than or equal to 2 such that vj, the jth vector, is in the span of v1, v2 up to vj minus 1. That means the vectors before vj. And the third property, there is an index j greater than or equal to 2 such that the span of all the vectors L, let me write this down, how it looks, v1, v2, and then this is about j index, so at some point you have vj minus 1, then you have vj, then you have vj plus 1, and then you continue up to vm. So this span equals, and that's the main part of the statement. The first part was just an explanation that L is the span of all vectors. So this span equals to the span of all the vectors except vj. So what we do is we go v1, v2, vj minus 1, and then we skip vj and we have vj plus 1 and vm. So here there is no vj. That's the big thing. So this is the statement, and the proof goes, so this is about equivalence of all these statements. 1 is equivalent to 2 and 3 is equivalent to 1 and 2. So the way we prove this with implication that goes around in circle, so we will prove that 1 implies 2, 2 implies 3, and 3 implies 1, and that closes the circle. This is the plan. First we prove 1 implies 2. So we start saying that L is linearly dependent. If L is linearly dependent, then by definition the sum, as I goes from 1 to m, ai vi equals to the 0 vector for some ai in the field with at least one non-zero a. Say aj is different from 0 for a specific j index. So the idea is then that if aj is different from 0, then we solve this as an equation. We can solve for vj. So this is a linear combination. It's very simple to solve. So you rearrange, you take all the other ai vi to the other side with negative sign, and then you divide through with aj. While strictly speaking, in general in fields, the division with aj is multiplication with AJ inverse. So we would have something like minus AJ inverse A1 V1 on the other side, plus minus AJ inverse A2 V2 on the other side, and then the last one is minus AJ inverse AM VM, which is almost what the second one says, that Vj is in the span, and the span means that Vj equals some kind of linear combination of these vectors, let's say Ci, Vi. The only problem is, so the span has these linear combinations. The only problem is that what the second says is a little bit more than what we have. We also have linear combinations here, but we have linear combinations going up all to M index. And this one says that the linear combinations should supposed to stop at Vj minus 1. So the I index supposed to go up to j minus 1 only with the linear combinations. So right now we have almost the second one, but not exactly. But at least that would be the idea, that if Aj is not 0, then you should be able to solve for Vj, because you can divide through with Aj. So we need to modify this part a little bit. The only reason why I wrote it down, because I think it's easier to understand this part, how you would solve. For example, if you have 2v1 plus 3v2 plus 5v3 equals 0, for example, if this is not 0, then we can write that v2 is minus 2 over 3 v1 minus 5 over 3 v3 after dividing through with v3. But again, that's not what we're supposed to have. The index not supposed to go up to higher index than the j, that's what we want. So we have to modify this proof. We choose j to be the largest index such that aj is not 0. That means that what we have is that aj plus 1, aj plus 2, and all the other higher indices coefficients are 0. So that means that we have this, from the linear dependence, we have this 0 vector as a linear combination of all the vectors, but then only the combination from 1 to j matters, because the others from I equals to j plus 1 to m are all zeros. So this part is 0. It doesn't matter. And then now that means that j is the largest index, so this looks now much better, because then Vj can be written as this minus aj inverse a1 v1 up to a j minus 1 vj minus 1. So that means this is a linear combination going from 1 to j minus 1, and that means that this is in the span of v1 v2 vj minus 1 as property 2 wants it to be. So this is almost 2, and still this is not 2. Let's see what 2 says. It says that Vj is in the span of V1 Vj minus 1 that we've shown. Now the only thing missing is that this j is supposed to be larger than or equal to 2. So the question is it possible that j is not larger than or equal to 2, but j is 1? So we also need that j is greater than or equal to 2. So this comes out from the fact that at least 2 a's must be non-zeros. If it's only one aj, for example, a1 is not 0, and then all the others are zeros, then we would have the linear combination giving 0 vector from linear independence all the a's are zeros except the first one, so we would have a1 v1 equals to the 0 vector. And we know that a1 is not 0, but then we had theorem 2.2.1 saying that if a scalar product of a vector is 0, then either the scalar is 0 or the vector is 0. So if the scalar is not 0, that means that the vector v1 must be 0, which contradicts the fact that none of the vectors supposed to be zeros. That was also a condition. Non-zero vectors. So that means we cannot have this case that we have one 0 vector. That means j must be greater than or equal to 2. At least 2 indices are not zeros. And this now really finishes showing that 1 implies 2. Next we show that 2 implies 3. So the second one, we assume that Vj is in the span of V1, V2, Vj minus 1, the previous ones, and also that j greater than or equal to 2. Then let V vector be an element in the whole list span, which is the span of all the vectors v1, v2, vm. So this is true if and only if, by definition, v equals to the sum as I goes from 1 to m, linear combinations ai, vi. If vj is in the span of v1, v2, vj minus 1, that means that vj equals to a linear combination bi, let's say bi, vi, I goes from 1 to j minus 1. That's the definition of a span, linear combinations. And then combine these two together now. Let me write down what V looks like. So we have in V, in this sum, we have the summation going to j minus 1 first. So we separately write down, and then we have aj, vj from this sum. And then we have the rest, where the index I goes from j plus 1 to m. And now we can substitute this vj, and then we obtain the following sum: I going from 1 to j minus 1, ai, vi. Then let me multiply aj into this sum. So then we will have I going from 1 to j minus 1, because that's also the index here for vj, and then aj multiplying the bi coefficients, and then we have the rest as before, I going from j plus 1 to m, ai, vi. Then what we see is we can combine together these two sums because the indices are the same, going from 1 to j minus 1. Let me write this down, the combination of all this. So we have ai and then aj multiplying bi. This is the scalar coefficient of vectors vi. And then plus we have the rest from j plus 1 to m, ai, vi. Alright, but then what do we see here? Let me denote this with ci, and actually this one also ci. So we have all the vectors I going from 1 to j minus 1, and then from j plus 1 to m. So this is a sum of the form ci, vi, linear combinations going from 1 to m, except there is no jth term. So we have I is different from j. What does it mean? It means that this is in the span of vectors v1, v2, vj minus 1, vj plus 1 with no vj up to vm. Since here we don't have the vj. What we have shown here is if a vector is in the span from 1 to m, then it's also in the span from 1 to m without Vj. When you show that something in one set is also in another set, V was arbitrary, so that means that this is true for all V from the span of V1, V2, Vm. When you show things like this, what this shows is that the span of V1, V2, Vm is a subset of the span V1, V2, Vj minus 1, no Vj, so the next one is Vj plus 1, Vm. The other direction that the right hand side set is in the left, so this kind of inclusion is trivial. If you have V vector in the span of these V vectors with no Vj, then that means that V can be written as the sum as I goes from 1 to m Ci Vi without the j vector, so I is different from j. But then we can also write this in the following way: I going from 1 to m Ci Vi, if we don't assume that the jth vector is missing, but instead of that we say that the Cj is 0, then that means that it's not that Vj is missing, but its coefficient is 0, so practically it's the same sum as before. And while this previous one wasn't in the span of whole vectors, or it is, because now we see that with some special coefficient we get a sum which is in the span of all the vectors including j. So here Vj is included, but with coefficient 0. And then when we have both direction of inclusion for subsets, so one set is a subset of the other is a subset of the first, that means the two sets are the same, which is exactly the third property, stating that we have this index j greater than or equal to 2 such that the span of all the vectors Vj is the same as the span of all the vectors without Vj. The last part, to show that 3 implies 1, if the span of all the vectors V1, Vm equals to the span of all vectors but with no Vj, here we have Vj, that means Vj itself is in this set, and then this set is the same as the span of vectors without Vj, so that means that Vj is in this set, and the definition that Vj is in this set means exactly that Vj is a linear combination of all the other vectors. And if you check what the first condition was, well, it's that L is linearly dependent. Well, how does this imply that L is linearly dependent? All we have to do is rearrange this and get the 0 vector with Vj on the other side. So what we get is A1 V1 plus A2 V2, then we have Aj minus 1 Vj minus 1, and then for Vj on the other side that will be negative 1 Vj, and then the rest of the vectors Aj plus 1 Vj plus 1 all the way up to Am Vm. And since at least one coefficient is not 0, that means this is a non-trivial linear combination, and if a non-trivial linear combination of a list gives you the 0 vector, that means this list is linearly dependent. So this finishes the proof of 3 implies 1, and then this finishes all the equivalences of the three statements.